Today I'll be talking about baby PIH and average baby PIH. So here's an outline of my talk. First, I'll introduce some background on parameterized complexity and constraint satisfaction problem and parameterized inapproximability hypothesis. After that, I'll average baby PIH. And finally, I'll give a quick overview of the two proofs. Okay. So first of all, why do we study parameterized complexity? One reason is that it's a way to cope with NP-hard problems. So given that problem, we associate each instance x with an integer parameter k. K is typically much smaller than input size, and then the time complexity is measured as a function of both n, the input size, and k. We say a problem is in FPT even if it admits an fk Polynomial time algorithm for some computable function f. Here f could be arbitrarily large, like 2 to the k. So we can take k-vertex cover as an example where you are given an undirected graph G together with a parameter k. And so when parameterized by the solution size, the goal is to decide whether there are k vertices that cover all the edges. This problem is NP-hard, but there is a 2 to the k times Polynomial time enumeration algorithm. We can just pick an arbitrarily uncovered edge and decide which endpoint to include in our solution. And thus, k-vertex cover, when parameterized by the solution size, is in FPT. For another problem, k-click, it's not likely to have an FPT time algorithm. And in fact, assuming ETH, there's no n to the little of k algorithm. People have identified k-click as a W1 complete problem. And it's widely believed that W1 is not equal to FPT. Okay, so given the nature that some problems are hard even with parameterization, so what can we do with them? And next idea is to do parameterized approximation. So can we find a GK approximation algorithm in fk Polynomial time for any computable function f and g? For example, can we find a clique of size k by 2 in a graph which contains a k-clique? Here's an example of parameterized approximation. In 2019, Cohen, Haddad, Gupta, Kumar, Lee, and Lee showed an 1 plus 2 over e plus epsilon approximation algorithm for k-medians and 1 plus 8 over e approximation algorithm for k-means. These two ratios are optimal in the FPT world, but in the NP world, the state-of-the-art ratios are just 2.611 plus epsilon for k-median and 6.357 for k-means. So this is an example where FPT time really helps to design better approximation algorithms. On the other side, we also have parameterized the hardness of approximation. In the recent several years, there has been a long line of work in this area on problems like k-stat cover, k-click, max k coverage, and so on. However, these results are somehow obtained via ad hoc reductions, and they are often tailored to the specific problems. So we may wonder whether can we have a unified and powerful machinery for parameterized inapproximability. In other words, can we have a parameterized PCP type theorem? Let me recall that in the NP world, hardness of approximation results are often obtained via the PCP theorem, where people first establish the constant inapproximability for the constraint satisfaction problem, then reduce CSP to many downstream application problems in a gap-preserving way. Let me define the constraint satisfaction problem. We are given a tuple x, sigma, and phi, where x is a set of variables, sigma is the alphabet, and phi is a set of constraints. The goal is to decide whether there is an assignment to all the variables that satisfy all the constraints. The gap version of CSP asks to distinguish between the case where value equals to 1 and the case where value is at most delta, where value is defined to be the maximum fraction of constraints that can be simultaneously satisfied by some assignment. So let me know that there are many examples of CSP, like 3 coloring, 3 set, 3 ling, and so on. But in this talk, we'll only focus on RT2 CSPs. That is, each constraint only involves 2 variables. So the PCP theorem states that for any constant-sized alphabet, there's no polytime algorithm for 1 versus 0.9 gap CSP, assuming p not equal to np. Here, the alphabet can be any constant, and the soundness 0.9 here is not important. It can be made arbitrarily small by parallel repetition. So how can we generalize CSP into the parameterized world? We define parameterized CSP as follows. Everything else is the same except for we set the parameter k to be the number of variables, and we let the alphabet size to grow as n. Why do we define parameterized CSP in this way? Because it's a natural generalization of multicolor k-clique. So suppose you are given a multicolor k-clique instance. So you have k groups of vertices, and the goal is to pick 1 vertex from each group so that they form a clique. You can build a variable for each group of vertices, and the alphabet just represents which vertex you can pick. Then you can use the constraints between different variables to check whether there's an edge between 2 vertices. So parameterized CSP is just a reformulation of multicolor k-clique, which is W1 complete. So as a generalization of the PCP theorem, we have the PIH here, which says such parameterized CSP is hard to, cannot be constant approximating in FPT time. Okay, so the current status of PIH is as follows. The final big goal would be proving W1 not equal to FPT implies PIH. And it was known by Iridineur and Passin that gap ETH implies PIH, where gap ETH says constant approximating max reset requires exponential time. Last year, we proved that ETH implies PIH, and Yichang will talk about this in the next talk. It was further improved by Bafnar, Minder, Karthik, and us in terms of smaller parameter blow-up. Okay, next, let me define baby PIH and average baby PIH. So we first discussed the least satisfiability of CSP. Now, instead of assigning 1 value to each variable, we are allowed to assign a list of values to each variable. And now, a constraint on 2 variables x and y is said to be satisfied if and only if there's a pair of values u and v, where u comes from x's list and v comes from y's list, such that uv satisfies this constraint. Here's an example on 3 variables and 3 constraints. The alphabet is 0, 1, 2, and 3, and the 3 constraints are shown as above. We can see this CSP is not satisfiable because x1 has to be equal to x2, but x3 poses different constraints on x1 and x2. However, this CSP can be least satisfied by the following assignment. We can assign 1 value to x1 and x2 and 2 values to x3. So you can see every constraint is satisfied by some pair of values in their respective lists. Okay, we say a 2 CSPs are least satisfiable if there is a multi-assignment with maximum list size R that least satisfy all the constraints. 2 quick remarks here. First, CSP value is 1 is equivalent to say the instance is 1 least satisfiable. And as R grows larger, it becomes easier and easier to R-list satisfy an instance. Second remark is, if an instance is R-list satisfiable, then we can randomly pick one value from each variable's list, thus in expectation satisfy at least 1 over R squared fraction of constraints. This means the CSP value, the normal CSP value must be at least 1 over R squared. In 2022, Bartle and Kozik proved the following Baby PCP theorem. For any constant R greater than 1, it is NP hard to distinguish between two CSP is one list satisfiable or not even R list satisfiable. Why do we call that Baby PCP? Because it's a direct implication of the normal PCP theorem. Thus, it is easier to prove than the normal Baby PCP theorem. So Bartle and Kozik gave a fully combinatorial proof, which is very simple for the Baby PCP theorem. And they also showed Baby PCP is already enough to get us some NP hardness of some promised CSPs, like 2 plus epsilon set. Okay, so we proved Baby PIH, which is the parameterized analog of the Baby PCP. So assuming W1 not equal to FPT, distinguishing between one list satisfiable or not even R list satisfiable for parameterized 2 CSP cannot be done in FPT time. Note that unlike PCP theorem, we still don't know how to prove PIH in a parameterized world. So first, Baby PIH is an itself interesting approximability result for list satisfiability of CSP. Also, it is built on the minimal hypothesis W1 not equal to FPT. So we hope that that is a baby step towards final proving PIH under W1 not equal to FPT. And can we get some applications of PIH just from Baby PIH? The answer is yes, but we need some stronger version of Baby PIH called average Baby PIH. This is recently proved by Liu, Chen, Li Ling, and Zheng. And as we show later, it is enough to get us some applications of PIH just from average Baby PIH. Okay. So in Baby PIH, we care about the maximum list size, but in the average Baby PIH, we care about the total number of values. In other words, the sum of the size of all the lists. An average Baby PIH just says distinguishing between satisfiable or not even satisfiable by multi-assignments with total value t times the number of variables. So on average, every variable gets t values. Even this is not possible to satisfy an instance. So here, we are just replacing the L infinity norm with the L1 norm. That's the difference. Okay. So the average Baby PIH is sandwiched by PIH and Baby PIH. And it implies the constant inapproximability for k exact cover problem and k nearest code word problem under W1 not equal to FPT. Okay, let me give you some overview of the proofs. The proof of Baby PIH follows from and extends Bartle and Kozik's proof for Baby PCP theorem. We use the simplest direct product construction. So given a 2 CSP instance, we take its t-wise direct product, where t is some large constant. So now the variable set is the set of all t-sized subsets of x. And the alphabet is sigma to the t, which is all the partial satisfying assignments for that set of t variables. By partial satisfying assignment, I mean the assignments on that t variables which satisfy all the induced constraints. And the constraint is simply consistency check. So 2 different size t subsets should agree on their shared variables. We want to show that for any constant r, there exists some large enough constant t, which depends only on r, such that if pi is satisfiable, then so is pi to the power of t, if pi is not satisfiable, then pi to the power of t is not even R least satisfiable. Note that here t only depends on R, so t is a constant, and our reduction runs in time n to the power of t, which is n to the O sub R of 1. So this is actually a polynomial time reduction, not FPT time. In other words, we get a unified proof for both Baby PCP and Baby PIH. Let's see an example. So here's a 3 list satisfying assignment for pi to the power of 4. There should be 10 choose 4 many variables, but due to the page limit, I only draw some of them. And we can see every consistency check constraint is satisfied by some pair of assignments for each size t subsets, for each pair of size t subsets. Okay, so the proof idea is as follows. We first take the R list satisfying assignment for some sufficiently large t. Then we want to extract some smaller instance t prime. We want to get a list satisfying assignment for pi to the power of t prime from pi to the power of t. If we end up with one list satisfiability for some pi to the power of at least 2, then we are done, because every RT2 constraint is contained and checked within some size t subsets, and being one list satisfiable means the assignment is globally consistent. So our hope is to decrease R by 1 at the cost of decreasing the exponent t. For each smaller set of size t prime, we pick its superset t from the original size t sets, and we inherit the whole list sigma t to be the new list of assignment to the sigma prime of S. So if we just do this, then the list size is unchanged since we inherited everything. So the clever step in this proof is to choose the superset t in some way such that we can always decrease the list size, maximum list size by 1. Okay. So due to the time limit, I'll not go into more details. And let me introduce the proof overview for average Baby PIH. So the proof of average Baby PIH is more interesting, and it is a self-contained black box reduction. Let me first show you a lemma. Fix any error correcting code C with block length n and relative distance 1 minus epsilon, 1 minus delta. Then any subset of code words that collides on many positions must have large size. What does this mean? So by collide, I mean there exist 2 code words that agree on this position. So if for more than epsilon many positions, I can find 2 code words that agree on this position. Then I can say the set S must contain a lot of code words. The proof is a simple counting argument, because any 2 different code words by their distance agree on very few coordinates. So in order to collide on many positions, you must have a lot of code words. Then here's a construction. Given a 2 CSP instance, we build the following k by n matrix, where the rows are indexed by the variables x1 to xk, and the columns are indexed by 1 to n, where n is the length of the error correcting code. And our variables are divided into 2 parts, A and B. In part A, we build a variable for each constraint in pi. For example, for phi 1, which is on variables x1 and x3, we build a variable a phi 1. And such a variable is supposed to take the encodings of the 2 values. So a phi 1 is supposed to control the 2 green pink rectangulars. And here's a phi 2, which is on x2, x5, and A phi 3, which is on x3, x4. In the B part, we have one variable for each coordinate, which is supposed to record the column of that matrix. So every A variable has alphabet f to the 2n, where every B variable has alphabet f to the k. Our constraint is just a row-column consistency check. The completeness case is easy. So suppose you have a satisfying assignment for the original instance. You can just write down the encoding of each variable in rows, and then read out the values of each column, set them as the assignment for B. In the soundness case, the idea is to argue that fix any average R list satisfying assignment. We either have a lot of positions J such that sigma Bj contains more than R values, or the collection of A part is super large. This way you can see either we have 1 minus epsilon times R plus 1 total values, or the value is more than what we selected from A part. Okay, so suppose for contradiction that for more than epsilon n many positions, sigma Bj only contains at most R values. Then we can argue the collection of A parts has a collision on position J. Then by our previous lemma on the collision number, it must have picked more than some root 2 epsilon over delta many code words from the A part. Okay, so here's some takeaway. First, PIH, parameterized inapproximability hypothesis, is a parameterized analog of PCP, and Baby PIH is the inapproximability of the least satisfiability of parameterized 2CSP. It says it's W1 hard to distinguish between one least satisfiable and not even R least satisfiable. The proof idea is to do induction on the least size. And average Baby PIH says it's W1 hard to distinguish between one least satisfiable and not even average R least satisfiable. Proof idea is to use error correcting code with large collision numbers. And as an application, average Baby PIH implies the constant inapproximability for K exact cover, which I think is not known before under W1 not equal to FPT, and also K nearest code word problem. That's all of my talk. Thanks.
Questions? So the average Baby PIH part, it's not a polynomial time reduction. It blows up exponentially in K, right?
Yeah, it's FPT time reduction.
There's no hope of doing similar things in the NP world.
Yeah, I think so.
Any other questions? Otherwise, let's thank Xuandi again.